Now in this video, I would like to describe the methods of describing the fluid motion. So whenever our fluid flows, its physical properties such as velocity, pressure, temperature, stresses or shear stresses vary as a function of time within a certain spatial region. So we need methodology or approaches to describe such variations of fluid properties. So there are generally two ways exist to describe the fluid motion. One is called the Lagrangian approach and other is known as the Eulerian approach. So in Lagrangian approach, the observer follows all fluid particles and describes the variation around each fluid particle along its trajectory. So in this approach, we go and trace each particle individually. So this is like can be described as sitting in a boat and drifting down a river. Now in Eulerian approach, the variations are described at all fixed station as a function of time. So this is like sitting on the bank of a river and watching the water passes the fixed location. Now next I would like to describe the concept of path lines. Why we need that? We would like to know, in addition to the properties of the fluid, that where the fluid is going. So to accomplish this, we trace the trajectory that a fluid particle follows while moving from one location to another. So for example, if it is my fluid element at this location and it is following a path while moving from one location to another, then I will call this my path line for this fluid element. So in this regard also I would like to explain another concept, which is a streamline. So a streamline is a curve that traces the motion of the fluid element, but it is more towards the vector oriented. That is, if I have for example airfoil and fluid is flowing in that direction, so each line is tracing the fluid motion. However, for my streamline, the tangent at a point is in the direction of the velocity vector. Each point, if I go and draw a tangent, so it will be my velocity vector for that. Each point, velocity vector. The tangent will be velocity vector for that. So if that is the case, then this line will be my streamline. Also make sure that streamlines are equal or same as that of path lines only for steady flow, for steady state flow, which is most of the time we will be talking about in this course. Here I would like to mention another term that we utilized in our fluid dynamics, which is known as kinematics. So this is a pretty common term that also utilized by people who are working in the structural dynamics. So kinematics is the study of the geometry of motion, and kinematics is used to relate displacement, velocity, acceleration and time without reference to the cause of motion. So for example, if I have a lump of fluid and it is traveling from one point to another point, and for example phi is the property of it, and these are velocities in u and y direction, then change in this property will be at some other time will be this d phi. and so the velocities will also be changed. So u will be u plus du and v will be v plus dv. So see that this element has traveled a distance. For example, call this distance dx in the x direction, and in the y direction approximately this is dy, the distance. Now I want to calculate the change in the property phi. Okay, I want to calculate the change, which is d phi. Okay, so this d phi is depending upon two parameters. The first one is time and the second one is the location. So next I will show you how to do that. Now, as I mentioned, the change in property phi, which is indicated by d phi, is dependent on time and coordinate location of the fluid element, and mathematically I can write that phi is a function of location and time. So the change in phi can be expressed as this mathematical equation, which can be further simplified. Now dividing both sides of this equation will result in this form, d phi over dt. So rearrangement of term. Here I would like to mention that this d phi over dt can also be represented by capital D phi over capital dt, and this is the right hand side of the equation. So subsequently, from the kinematics, I will introduce these two definitions in the above equation. Now subsequently, the equation can be simplified as in terms of velocity components u and v, and it can be further simplified and can be written in terms of the dot product of del operator and velocity vector. So make sure that this del operator has two component and similarly the velocity, this is del operator, okay, and similarly the velocity vector has two components, so ui plus vj, and the dot product can be written like that. Here I would like further to expand the definition of each term in this. So left hand side is commonly known as the total or substantial derivative that you can take for any scalar or vector property, and in the right hand side we have two terms. So the first term I should say is the local derivative of that property, and the second term is the convective derivative of that property. So the total derivative is the time derivative, which is carried out as one follows the particle or the lump of fluid. Now the local derivative is the rate of change of that property with respect to local time, and convective derivative change due to the fact that the element is moving in a field of varying property. Now as an example, for example, if I have a velocity field, a property velocity field given by this vector, and I want to calculate the change in this, the total change or substantial derivative, then I can utilize this formula or this operator of my total derivative to find the change in that property. Utilizing this equation, I can easily find that.